Hello, everyone. Thanks for joining the session. Welcome to our day zero session one. The very first session of our machine learning series. Some of you may have joined the Meetup Live session that I conducted a few months back, and unfortunately had the live recording corrupted. So I'm re-recording and sharing on my channel. Don't forget to subscribe as PDF notes and the GitHub link will be shared with the subscribers for all videos that I share going forward. So let me quickly introduce myself. I'm Maitri Sinha Chaudhary, a tech enthusiast and a leader. And Chrysalis Innovation is a knowledge sharing platform focused primarily on technology related to data, ML, AI, and other emerging technologies aspects. So, as a way to giving back, I share my knowledge in few platforms, which includes Meetup Live, mentoring organizations, and in this, and also open to others who would like to share their knowledge in this platform. And again, a few points before we start. We're not a training organization. We will not sell a paid course in my community, and any engagement with this platform not going to involve any financial transaction for teaching. So let's figure out what do we have in store as a topic for day zero, basics for AI and ML. So first of all, we will cover basic understanding of artificial intelligence, machine learning, and deep learning. We're going to demystify the similarity and the differences among the three. We're gonna talk about a bit on always a bit because anyway it's a basics course. Basics I wouldn't say course, basics session. So you wouldn't have a deep dive in most of the things. It's very much of header level information that I'm gonna talk about as of today. So yes, traditional programming versus AI, ML, and why we need ML. We're also going to talk about basic terminologies related to AI and ML. Now, that may be very familiar to the people in here who already an expert, but there are people who are actually, not aware. And if I don't clarify those terminologies right away, there is a chance that the further conversations may seem a little, sketchy for those set of folks in the session. So also, what is it the basic requisites for an AI, ML, and DL to run in any system, in any backdrop? What do we need for an AI to run, right? Also, we're going to focus on there are basic four pillars of any AI or machine learning or deep learning tasks. We'll talk about the high level basic steps in implementing. Again, we're going to conduct another session, which is the next session, which focuses on all the sub steps, double clicks of each of those high level steps. But let's talk about if I has a block level, what are those steps that definitely needs to be in an end to end machine learning implementation project. What are the different types of ML, machine learning system or task? Or what are the types of ML systems that we can say and how those are categorized is another approach. What are the examples in daily life we see? There is a chance that a lot of you are using it very much close knit attachment to those apps and devices and all, but you never really realize that you are actually this close using an AI in your day-to-day life. And also, we will take a surface level glance on how the responsible AI and the governance pillars associated with. So far, so good. Okay, now let's start. Right? This is our main topic: basics of AI ML and define, DL. So if I define it as a very surface level, remember it's day zero. We'll not get into the criticality yet. Now, what do you mean by artificial intelligence, right? You can say it's anything. right? That allows a machine, or you can say a field of study that allows a machine or thing or app that can mimic natural intelligence will get deeper but hold your thoughts, right? So, what is ML? ML is not a capability. ML is a statistical technique or a mechanism that AI uses, right? It's the ability of a machine to learn from structured data using various statistical trainings, techniques and algorithms. It predicts the future based on past experience or past data points, rather, right? Now, when it comes to the DL, what do you say? It's a subset of ML. By the way, I will talk about it. It's not always a subset of ML, but usually you can say that a DL is an, I would say subset in the sense that not in terms of properties or features of a deep learning method. It's more in the sense of um, it's an advanced machine learning method that allows multi-layered learning for prediction. For example, it in the areas of natural language processing, computer vision, generative AI, transformers, right? Now, before I talk about the relationships and all that, one thing is that it also deals with unstructured data mostly, right? So let's move on. We just discussed in one or two liners what these areas mean. So we discussed that an AI is, you can say, a capability or a field of study. We discussed ML is a process, or I mean, if I would give you an example, right? If AI is a, you know, I would say it's a dish, right? You can say ML is the, I mean, if AI is a dish, ML is a specific kind of recipe, right? And DL is more enhanced recipe. But in both cases, the chef AI or the dish AI is using, or I would rather call it AI as a chef, which is using the two different kind of ingredients, which may be connected, may not be connected, but using these two areas to build something, right? So build the dish or make the dish, right? So relation. So roughly, if I say, what is a relation? What is the similarities that we can discuss, right? So anything or app, an action that can mimic human intelligence, right? AI uses ML to build the ability to mimic human intelligence. You understand? The relationship is, they're not same thing. They use each other. They are connected to each other. I would say symbiotic relationship wherein AI uses ML to build the ability, right? So you can say an example. ChatGPT learns from response. ChatGPT itself is an AI capability, but then it uses the transformer classes, right? It's uses, right? So self-driving cars learns from cameras, sensor data, algorithm. Again, these are AI can be ML, the AI can be deep learning, AI can be a normal traditional programming, as in, as you can see, right? And ML actually can, I mean, AI actually can exist without ML, as in AI to mimic an intelligence, mimic a natural intelligence. And AI may or may not need machine learning, right? So let's see that. A method where machine can learn from structured data, and also it deals with the classic algorithms like linear regression, decision trees, random forest. Primarily deals with, I mean, the input data for for these kind of tasks. You can actually work with a table or a file, so it's not going to be a problem. ML is a subset of AI. Again, I will discuss this. ML is subset of AI, yeah, because AI, as I say, can exist without a machine learning deployed, or even without deploying a deep learning. But at the end of the day, you know, the relationship is AI can use ML. So, like for example, Netflix recommendation from their viewing history and suggest shows and movies. This is the you know uh, ML task, right? And AI, the suggestion, the recommendation itself is the AI power. When we say AI powered, AI capable, is basically nothing but an ability that is mimicking almost like like let's say some app is suggesting you go for this recommended show. Well, it's not somebody, a human being is suggesting, it's an app suggesting. But how it is doing that? It is doing by performing, running some classic algorithms. I will not talk about collaborative filtering and all that at the moment. But let's talk about as an overall. It can use ML workload and find out what should be the best recommendation for you. So you can say this is how AI and ML connected together. There are a few more examples such as fraud detection. You can say spam filtering of email. These are general examples that I can talk about at the moment, right? So that is machine learning. Let's talk about the relationship with the deep learning. Now, with the deep learning is again anything or app that can learn deep multiple layers of statistical decisions, like we have humans, neural network, like our brains have a neural network. Similarly, they have, you know, it's if you imagine, right? Even though we will not go deep into the DL, go deep into the deep learning method, but ideally, the idea is that like some of us who have a complex thinking ability, especially people say women think complex. Well, different networks, how our brain is wired, how our brain is it densely wired or is it kind of sparsely wired, depending on how smart we are, how much our the synaptic connectors are working. Ideally, what we can say is that every layer of our in the network of thoughts, every layer is performing some kind of calculation, and that is passed on to the next layer. So that's why once as we think, more thinking keeps coming up, more thought process, more deep analysis comes up. So that's how machine can also do the analysis, and a propagated thinking can be possible, and that is what is the deep learning is. So again, can deep learning be subset of ML? Probably sometimes. Sometimes actually it is not. It can be very mutually exclusive, separate area, even though the diagram I'm showing as part of it. Part of it, in a sense, as I said, part of it is because it's an advanced level of machine learning. But then again, it may be very different kind of beast because it's dealing with the unstructured data, you know it's dealing with your such data such as audio, text, video, images, speech, right? And it has a different kind of neural networks for different kind of workloads. We will talk about those basically. CNN, RNN, recurrent network, neural network, convoluted neural network. So they have different kind of algorithms for deep learning, right? And as I just said, both ML and DL are used by an AI capability. So you can say AI again is the chef, and ML and DL you can compare them to two different kind of maybe veg, non-veg, or advanced, gourmet or traditional um, recipe. And ingredients for those recipes are also different. One is the gourmet is dealing with a lot of special kind of ingredients, superfoods, blah blah. Whereas the traditional food is using local vegetables, local ingredients, and AI is using these two different kind of recipes to build or make different kind of dishes for different kind of consumers, as in different kind of workloads or problem statements. So you understand how it works. So far with me, right? Example again, facial recognition, wherein different data points on an image is utilized, like Face ID or surveillance systems can be you know utilized for this. Autonomous vehicles, they use video feed and sensor data, right? So that is also another area where deep learning is used. Language translation, and also there are other areas such as Gen AI is also another area, transformer classes, that AI as a study of field, or a AI as a capability, is using these. Hopefully, you're clear. So an ML is an AI. I mean, ML can be used in AI. That AI can exist without an ML. That's clear. And any deep learning is ML, and any ML may not be DL. Again, I think I will little bit correct myself. Any DL, any deep learning may or may not be machine learning. There is you can say there is an intersection area, but it's not exactly a subset of that. I think I should change my diagram for that. But I've explained this, right? So AI uses ML, DL, traditional program, right? It's a more precise when it comes to this relationship, right? Agree? Um, any question if you have, you can add it to the, what do you call it? You can add it to the um, comment section. You can add it, right? So yeah, so I can say that this is ideally what I can say for the relationship. It uses traditional program through rules. It uses ML through structured data. I mean, it trains ML models through structured data. It trains DL models through unstructured data. That's very good. Let me grab some water. Okay, now coming to that next, right? So I'm going to discuss about ML framework and model architecture. Just keep an eye on it. Don't think too much about it. I'll explain as we see. These hardware, right? Now, differentiation of in AI, ML, and DL. So, if we run through the areas where AI, ML, and DL have distinct presence, different from each other, like I already discussed how they are related to each other, how they are connected to, what is the similarity. I mean, why it is important. Again, I've discussed why are we discussing this. Primarily because a lot of people use AI, ML as a buzzword. They use everywhere. Even a simple automation with a business logic or proper logic, mathematical logic, people say, oh, AI powered. No, it's not. AI powered is not everywhere, right? So again, do you need DL everywhere? Maybe not. So we'll discuss, and that's the reason why, rather than interchangeably using this, people should have a very clear understanding of when it is AI, when it is ML, when it is DL, when it is simple coding, right? So basically, if I talk about, there are few areas. Now we just discussed the relationship. Now let's few areas where they are different from each other. I think we already touched upon that, but I'll be very clear on those, right? So first of all, AI is, we just discussed that by definition, AI is not a technique. AI is a capability, right? It's capable of mimicking a natural or human intelligence. Could be a animal intelligence also. I think it's not human only. It could be any natural intelligence that AI is capable of mimicking, which basically means it's a capability. ML is a capability, but you can say it's a sub capability of learning from the data, right? So ML is not something that you would expect as a direct outcome to anybody. right? So as I again was giving the example, AI is the chef, right? You have a dish, the capability, the app that is using that AI is that dish, right? And ML is the recipe. This is how the food or the data will be cooked and the final predicted dish will be served. So you understand the definition, the difference definition wise, right? Now, what is the scope? AI is broad. It includes machine learning and deep learning, but it can also be achieved through intelligent coding. It's possible now, right? Machine learning is a subset of the AI. Machine learning used in AI. Deep learning used in ML sometimes, definitely used within AI. And again, similar to subset, similar to the machine learning, it's another recipe where, again, data dependence. Data dependence wise, AI may not even need data. It may need just a very intelligent rule. So if there is a business rule or a mathematical rule or statistical rule, you will apply that rule instead of really, if you know the rule, apply the rule. But ML comes in the picture when you don't know the rule, and I'll talk about it, right? So relies on structured data. Deep learning relies on unstructured data. Now, can deep learning be performed on structured data? Yeah, of course. Why not? Right? But usually, when you deal with unstructured, you know that you're going into the area of deep learning, right? Now, what are the example algorithms? Could be artificial intelligence, fuzzy logic could be there, rule-based systems. Any rule is a algorithm for it. It can even be customized. Machine learning is again classic algorithms such as and linear regression, decision trees, random forest. These are all coming under SVM. These are all coming under machine learning area, classic statistical techniques. And deep learning is where you have network perceptrons, multi-layer perceptrons, right? So convoluted neural network, recurrent neural network, different kind of transformer classes, Gen AI related, right? These are all coming into the deep learning algorithm wise. I have been saying this multiple times. I hope you are clear. What is AI? What is ML? What is DL? What's the relationship and how they are different from each other, right? And application wise, problem solving reasoning is where AI is applied. Machine learning does the predictions or the classifications for the problem solving AI needs to do. And deep learning also does the same thing, such as object detection or translation. So that is also serving the purpose towards the problem solving or the reasoning that the AI needs to do. Right. So ideally, this is overall you can say is a you know is a relationship. The demystification of these areas, right? And it's a bit stuck, right? So next question comes: why apply ML? Why do you need ML? I mean, I just discussed AI can be achieved through traditional programming as well. Well, why do I need ML then? Well, let's example. I mean, use an example to establish that fact. So, traditionalist programming is applicable when you first of all you don't have a lot of data. Number one, you actually um, don't have a lot of data to come up with something from the data, learn from the data. Number two, you know the logic. You know one plus one two, so you want to apply a certain logic. Now, if you know the logic, and you don't need a lot of data to apply that logic. You just need to add the logic to your code as a programming code, simple programming, traditional. And any data you run it by, it's gonna apply that logic and gonna predict some value. So you're good. You still are able to predict something, but with a static rule. It's not a dynamic rule, or even if it's dynamic rule, ideally you're not learning from the data and applying that. You simply know an equation that probably the business has been using, or maybe it's a very statistical formula that has been applied since ages old time. So you can apply those. So fine, traditional, you know, method can work. So as I said, traditional program is applicable when you know the rule and can dictate the solution behavior, right? You know what to know, right? So you need sample data to test. You really don't need a lot of data. You just need a little data and you want to test whether your formula is, up working. So it's as we have done it always. But machine learning is applicable when you don't know the rule and let the data unfold the best model for it. It's possible. Like, I'll give you an example. In my own organization, a lot of attributes are coming, and there is no real tracking of that data of how the derived attributes are coming. There is no documentation. There is no proper data governance is in place for some long period of time. So ideally, people don't know what the rule was. So applying machine learning to those attributes are able to derive a business logic, which is, I mean, basically it is saying, okay, all right, you don't know the rule, but looking at the data looks like this is the rule. Right? So in such cases, you should be applying ML. So you know that you don't want to use ML everywhere and anywhere. Just because you know Python, you don't want to apply everything and everything everywhere. So that's one situation where you don't know the rule and you can do it. Second, you don't have ample data. For some reason, you don't have enough data to learn from. Even if you um, have a problem with the rule, you don't have a lot of data. Maybe it's a new company, maybe it's a new process. So you don't have a lot of data to actually learn from. You need a lot of data, at least 100,000 records to actually start learning, right? So training will not be possible. So that's where you don't want to apply ML. Otherwise, if you have enough data to learn from, you will go for that's like unraveling the organic behavior of the data. So you don't have to rack your brain to come up with a rule. This system gives you the way to identify. Now, another thing that before I move on to the next slide, ideally, sometimes it's also possible that you know the rule and you have enough data, don't have enough data, but you know the rule. But the concern is that, let's take an example of spam filtering, right? Initially, even though it's now AI driven, that was a time when people used to identify what's the pattern of such emails, and they used to flag such emails as a marketing email or spam emails, right? Considering the subject line, the sub in the format, the specific characters, stars, free, 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 right? People used to identify that it is not a legitimate, it's not a useful email. But then, and even such emails, not just the marketers, it's also the phishing, scammers. They also do that. So ideally, what started happening, more you flag them, the scammers kind of understand that, and they you know, start applying those rules at their end. So you for something that you were avoiding, they're no more sending that. Sending something else. So how many times would you update your rules? But when it comes to you apply ML in such cases, it starts learning, right? starts learning from your email and how your behavior towards those email. Like you never open those emails, or you have set some rules to send it out, right? So it starts learning that, okay, you know what, these emails are not useful emails. These are bad emails, and starts learning from your data, and it starts appropriately tagging those emails as spam emails. So it's AI is where you don't have to keep updating. By the time you update your logic, the scammers have come back with something else. So these are the areas where it's hard to keep up, right? And if you allow the data to dictate you, there is a chance that you will learn more from the data rather than you becoming the Mr. Know-it-all, and you define a rule that no more even works, right? So that's why these are the scenarios where ML fits, right? As I said, problems where you have certain understanding of the solution rule, but not really can keep up with the changing backdrop, like spam email detection. Now, problems where the data set is large and situation or equation is complicated is also an area where ML fits. You don't want to do it with your own thought process applied, right? And again, as I say, the problems that can teach you over time that you won't know if you block this learning process by applying your own logic. More like, rather than telling my child what to do, if I observe what the child is doing better at, probably I'll be able to guide the child to a right direction rather than telling the child, yeah, this is the rule, this is what you will do. Maybe he or she is not going to do great at that, right? So it's like you can learn from the problem statements, from the data your model can learn and actually predict the right kind of tagging or right kind of classification here. In this case, examples. And simply where you actually don't know the rules to apply. Like the case that I said in my organization, a lot of business logics are missing and nobody knows. The older team members have left. So ideally, what happens? You are not able to apply. Above all, can be ML problems. Good. We discussed. Now let's move on. And now this slide may be more for the people who are very, very new to this concept. People who are already experts, they're all rubbing shoulders with all the other data scientists, may not be needing to know this. But I would, again, as I said, I will discuss a little bit of, spend a little time here only to ensure that people who are new, basically for whom this class is actually intended for, they can understand, because next time when we use those terms, it's not gonna, put them at off. Now, prediction is nothing but act of forecasting a possible outcome that we're trying to improve or be aware of. So, say I'm trying to predict my sales volume next year. Now, if it's less, I have to find out how I can improve it. If it's my revenue in next quarter, so these are the things I'm gonna predict. We will probably a housing price that I'm a median housing price that I'm trying to predict so that I can use it in a real estate investment. So ideally, you can say that this is the act of forecasting, right? So secondly, what is a model? You can say, what is she mean by model? Model is nothing but, in this context, right, equation or a proximity that presents a relationship between a forecasted outcome with multiple of or single influencing factors. Now let's understand. We all have, at least who are close to mathematical background, know y equal to fx, right? It could be linear, it could be non-linear relationship, but I'm saying y is the targeted value, the outcome that I require, and it's a function of multiple independent variables. So y, which is the dependent variable, whose values are dependent on the values that input variables need to be. Input variables are what? Those influencing factors or features. So let's take an example I am sad. Again, this is definitely mathematically not a right example, but I'm just giving you an example. If sad is the outcome, right? And if anybody could ever measure sadness, you can actually, it could be a function of multiple things. Could be a function of the relationship, finance, career, a lot of things, right? Function of all these features. Now, if it was possible to regulate these features, of course, your sadness score will go down. So you can actually regulate, right? Regulate your sadness by regulating other areas, these factors. Agree? Right? So once you can model these regulating factors in your life and you abide by that, of course, your sadness will be in control. So, which ideally means you will not be depressed, right? Your happiness score is high, your sadness score is low. Even anytime there is an alteration to it, other regulating factors are changing, and you automatically again becoming a happy man or a happy woman. So ideally, you have a better emotional health. Now, why I talked about all of that here, ideally what I mean is that statistically, an outcome is related to, is influencing factors through some relations, through some equation. And if, I mean, it would have been fantastic if we all could figure out the equation of life. We would have been all happy people. But yeah, in this case, anything that is mathematically possible to initiate, like sales volume, is maybe related to season, maybe related to distance from city, maybe related to a lot of things, right? So you can actually correlate, and I'll talk about those in another class, but correlate all of these factors and figure out how these are impacting the price points of your product, or your sales volume, or your revenue forecast. All these are related, right? So that's how a model works. Now, what is a feature? I just talked about a factor that influences outcome to a certain degree, right? Now, how much? That's what your algorithm helps you find out. Agree? Right. So algorithm is what? It's a statistical method that is help establish a relation between outcome and the influence factors. Now I just talked about there is an equation which is model. The x is the feature. You have a target variable which is the prediction. And then algorithm is the process, that formula which is establishing the relationship, right? Now, training, it's the process to keep the model relevant with new data on the features. Now, let's understand this part. If the process of training a model is similar to training your kid or yourself, forget about kid, yourself. More you keep yourself updated with new data, more relevant you are in the market, right? Agree? Similarly, when a model is established and sent to be utilized by an application, more the like ChatGPT needed a new release, right? So older releases, of course, it's not going to work out for a long time, right? So you definitely need they needed a new training process for the ChatGPT, right? And what I know that ChatGPT 3.5 is not really updated regularly, or I mean, as in it's not learning real time. Anyway, we'll talk about it. 4.5, I believe, does, but 2.5 is a static learning method. And I'll talk about this when we today itself. So, training is the process of teaching your model with new data so that it improves its performance and stays relevant, right? etc, because there are many more terminologies, but this is to start with. Now, what you need for ML? What do you need for ML? These are the four basic pillars that you need for any machine learning or a deep learning task to run. What are those four? One is you need data set. You need data. You need a lot of data to learn from. You need machine learning framework. You need a model architecture, and I'll talk about what these all are. And you need a hardware. These are four basic, or I would rather say main pillars for any of these tasks to, or any of these workloads to run successfully. So let's understand. One pillar, let's talk about data set. Now, I know, as I just discussed, and before even talking about the transfer learning, or the set of data sets that I'm showing here. Basically, let me I would say let me go a little deep on that, right? So ideally, give me 1 second. Sorry, I'll be back. Yeah, right. So data set is where. Give me 1 second. All right, I'm good. So it's a structured collection of data that is used to train and validate and test your ML models. Now, and ideally, this is the main thing that I've been talking about, right? We need ample data for a model to successfully be trained, and tested, and evaluated. Now, it could be labeled data set, it could be unlabeled data set, it could be a mix of the labeled and unlabeled data set, right? But I need data to learn from. Now, what is transfer learning? So, usually, as I was just discussing, right? So, for your ML model in a real life example, let's say you have to build the data from scratch. It's possible that you have need to build the data from scratch because, your I would say contextual data that you require may not be available anywhere. So you may need to build that data. But until the data is built, there is a possibility of some data that you can use from already publicly available open source data sets and train your model, at least initially, using those pre-trained learning. Whereas where it's not necessary for the data to be company specific, right? Like let's say an example, object detection. You want to identify all the animals. If that is your use case, you may be able to use open images. There are some list of videos and images you have, or even the text. Those are publicly available data sets that you can use. And then using this, you can actually, because, let's say an object detection. It's a very tedious and cumbersome and costly, time consuming process where actually sometimes it is, people are given a task, paid Fiverr folks to label data sets automatically. So because and I'll talk about those at the moment, just to explain. Those are needed to label because you want to use that as a reference point. Now, it's like when you're teaching your child, you're saying, hey, this is apple, this is orange, this is cat. Now, the baby is new to the world, right? And you are identifying. Your baby is a human, so it doesn't require millions of images. But at the same time, but your model is not, you're a human baby, right? So it does require a lot of images and requires a lot of labeled images. So labeled images is what helps, your algorithm to figure out next time that this is that object detection it requires, right? You unlabeled data set is also helpful in some cases where you don't tell your kid. Let's take an example. You're not telling it's a um, cat or dog or whatever. But then your kid automatically identifies when, say, your kid has been seeing you, and suddenly your older brother comes home. Your child automatically detects that person as someone related to you. That's my observation. Why? Because even though you have never told him it's your uncle, it's my brother, you haven't said that. But since you look kind of similar, right? Proximity to your face, she or he identifies, oh, someone related to dad. And he or she kind of starts connecting with that person as someone of her own, right? Uncle or, you know. So this is an unlabeled learning where you haven't told, but she already identifying the this is this is similar. Your model identifies, even though you provide an unlabeled data set, it still has the ability to relate proximity. And that is what you need for your, and I'll talk about that, clustering algorithms and all that. Mm. Second is a mix of data sets. So when you say mix of data sets, is what? I'll give two examples, one with the baby again and one with the actual application. Uh, so let's say you've actually shown your baby a white cat, right? A white colored cat. And you've told this is cat. This is um, some name of the cat. The baby understands it's a white colored cat, but when the baby sees a brown cat or a golden colored cat, she would still, you know, act delighted and say meow, which basically means she understands, even if you have not given a tagged image of a golden colored cat. Still, she was able to find out that it is a cat, even though you just showed her a white cat. So that means that once your model starts learning with the labeled data set, later on it is able to also use the unlabeled data set and relate to the few that you sent as a labeled ones. That's one example with your baby. Now you can actually relate how it works. Similarly, in an app, like I don't know whether you noticed, when in the Facebook, I think long time back, maybe in the Facebook only or where I don't recall, um, you had to tag somebody. If you're adding, you had to tag the right person. You have to actually tag the name of the person and then let Facebook know that this name should appear here. But later on, after a few times you have done that, automatically it would pick that name and say, okay, detect that this is this person's name with the photograph. So ideally means the automatically the algorithm has identified that this is that person's, this photograph belongs to that person who's also a Facebook user, right? So that's what I'm trying to say. Um, this is how data set, either already pre-existing data set that you can use through transfer learning, or you can build up your own system by consuming time, cost, whatever, and effort. And then finally, you come up with a data set that your organization needs to use for training your model. So you understood data set, how important it is. Now, and if I take an example, I always take examples. If you're building a house, this data set could be a brick, let's just say, right? Now, if I talk about the model architecture, which is the next part. Now, again, if it is something that your data set was the brick, right? Of course, this is your, I would say, the blueprint of your house. You have the brick now, you have the blueprint with you, right? So basically, this is defining how the model will process the data, right? Which basically which architecture you're using, right? Model architecture decides how the data flows through, right? The pipeline decides the model capability, efficiency, and effectiveness for solving a specific problem. And it also describes the configuration, depth, weights, biases, activation, and all activation function and all of that, right? Depending on which kind of neural network architecture you're going to use. So these architectures are tailored for specific tasks and domains. So different kind of algorithm, you can say algorithm again, model architecture is nothing but the algorithm that can showcase the versatility of AI across the industries, right? It's a blueprint for building a house. Now here are some examples, right? Which can be used for specific use cases. Like CNNs are usually used to deal with image recognition, object detection, medical imaging, as I said. RNN used for time series, speech recognition, sentiment analysis, right? Transformer architecture for NLP, chatbots, multimodal AI. So I'm not going to read all of it, but ideally it can tell you reinforcement learning for robotics, gaming, dynamic pricing. So, right? So for each of these kind of algorithms, there needs to be a separate class or a session on these. But ideally, you can understand these are the model architecture, and that defines how, as I say, this is the recipe. Last time also I mentioned, this is the recipe, your model architecture, right? Now, this is your AI is the chef, your data is the ingredient, or in this housing is the brick. This is your blueprint of housing. In kitchen example, this is your recipe, right? What comes under what? This is the recipe says, or this is the blueprint says, right? Now, third important framework is the um, ML framework. Now, what is it? I just discussed model architecture, which you said blueprint. Now, what is it? It is toolkit. What you will use. See, the point is, let's take an example. Same recipe. When my grandma used to cook, she used to spend a lot of time, a lot of extra effort because she didn't have the right toolkits with her, right? So she used to do all the manual efforts to come up with the same, same recipe, maybe more authentic taste though. But yeah, so there are some frameworks that I have given. I mean, there are some different task category wise and different, like let's say general purpose ML frameworks, which includes your image classification, object detection, classic ML activities, email, all of that comes under general purpose ML framework, right? Which three main ML frameworks or toolkits we can use: TensorFlow, PyTorch, scikit-learn. Usually scikit-learn is I use, but then you know TensorFlow is also another important ML framework that can be used, right? Deep learning framework, right? Again, image classification comes under that, NLP, real time object detection, all of that comes under deep learning framework. And there are things like Keras, MXNet, CAFE that can be used in these areas, right? And I've shared who they are built by. Similarly, the text summarization, entity recognition, you know, all of these space basically ML frameworks such as Spacey, Hugging Face, these are coming under the NLP, right? And you know, this is these set of examples that can tell you that now, do you want to understand how each of these tools work? No. Do you need to really go into the details of how the algorithms work? No. You need to know when to use what in combination of what. So similarly, do you need to analyze the recipe? No, follow the recipe. Do you need to know which recipe to pick, right? And do you need to know how internally these toolkits are built? No. You need to know to beat the egg, to whisk the milk, which kind of tool I need to pick, right? So these are the tools which would work with certain kind of model architecture, right? And you will have your desired results. You at the end of the day want only the prediction. You don't want to rediscover these, building blocks. Okay. Now, with that, it basically keeps the computations undercover and simplified and ready to use. That's exactly what I said. It's abstracted. You don't want to know all of that unless you are someone who is building these tools. If not, if you're using these tools, don't break your head. Efficiency, of course, something that you do manually, your grandma was doing. You're using a tool, it'll be more efficient if you know how to use the tool well, and you have a optimized resource for, right? Reusability. So of course, if it's not manual, it's easy to reproduce this activity multiple times because you have your toolkits, your blueprint ready, and your toolkits, right? Ready. So it's easy to now just jump into the work. You can scalability since it's tool driven. You can cook for entire guests. So ideally, it means the scalability is high for such ML framework. And at the end of the day, there is a community support. People are kind of, people may have faced the similar situation, so they might be able to help the solution that they had. Right? So community support is another thing that these frameworks support you with. At the end of the day, toolkit for building your house, you already have the data and the blueprint. Head. Now you have the hardware. This is what you. This is the component that decides what capacity and scale your learning process can truly run and what kind of optimization that can be achieved. Let's understand this, right? Now, one thing is clear that it's like you in the housing example. You had the brick, you had the blueprint, you had the toolkit. Now you also need the structures. It's in your um, bars, iron bars, your I would say the structure, the internal structure, the iron bars and rails and guards that you require at the end of the day for the structure to give you the foundation and on which your whole housing can stand. It's basically it's nothing but your ML platform, right? So the hardware becomes very important. Now there are four main areas of hardware type that I will talk about. One is your CPU, GPU, FPG, and ASIC. Now, what are those? Just quickly, look at the timeline, and then you will be able to clearly figure it out. So we've been using CPUs since 1970s, usually good for small scale ML, pre-processing, inference, etc. And IBM, Google, Intel still use it for their tasks like NLP, ranking, and all of that, right? Intel, AMD, Apple are major manufacturers, so to speak. So that is the central processing unit, and it's still we all use it for our general purpose activities, right? And a small scale AI, as I say, small scale ML or small scale AI, because at the end of the day, CPU cannot. I mean, you cannot really run a large workload with a large data on your local system. It's going to die, right? So ASIC, application specific integrated circuit, again has a it's not new. It's there since 1980 until now. And this is kind of, you can say, people are working closely on, making a very customized solution. For example, Tesla uses it for self-driving cars as an FSD chips. Um, uh, Again, Google uses it for their deep learning tasks. So using TensorFlow. So basically, ASIC can be used for all of these. And Google and Tesla are major manufacturers for these as well. Now, FPGA is Field Programmable Gate Array. It's again available since 1985, not new. Microsoft Azure use it for real-time inference. Again, 5G networks use it for AI-powered traffic optimization, and even Amazon EC2 F1 instances use it for scaled ML workload. And again, if I talk about the major manufacturers, it's AMD, Intel, Lucky Semiconductor are the few names as a major manufacturer of field programmable gate array. Now let's talk about GPU. It's interesting. Since 1999, or let's say 2000 onwards, when the Web 2.0 started taking off pretty high, like around 20 years back, 25 years back, you can say that chat apps, image and video, snap sharing apps that started becoming popular. And that's when, people did not, they wanted there was a shift in user behavior. People started expecting an image to be loaded pretty fast. They did not want an image or a video to be rendered taking a long time. And that's when there was a huge shift and evolution. I would say that a shift that changed how the user behavior and also the hardware manufacturer behaviors changed. They started focusing on hardware actually, which would allow faster. You know, Previously people used to build applications that would be supported by the platform. This is the time when platforms started being supportive of the app, right? So this is just a completely 180-degree shift in how market started, or the technology giants started responding to the customer behavior rather than the other way around. And that's where you can say that Nvidia and all those companies started coming in the Intel, Apple. They started becoming the major manufacturers of graphical processing units, and it is used worldwide. The ChatGPT, Tesla Autopilot, DeepMind, AlphaFold, these all use GPU for all their graphic, and I can also take another name, that is Boeing. Anything that needs to be rendering, not just AI, even a non-AI, but a simple rendering, image rendering or video rendering application, that's where the GPU started being used. So ideally, this is an area where hardware started becoming available or more customized or more, I would say, optimized for supporting specific user expectations of um, speedy image sharing, right? So sharing and also executing, or going deeper into the details, readability, and that, the I would say the resolution, being able to render an image to a HD quality is what something that the hardware organization started doing, right? And finally, 2015 onwards, Google brought in their transformer-based models, large workloads, and TPU, tensor processing units, is ideally supports TensorFlow, and there are other areas also that TPU can be used, but ideally Google is its main manufacturer. So roughly you can say how these are supporting. Let's talk about some of the real life examples, right? So if I talk about the real life examples, right? So now that we have some basic understanding, you know, quickly browsing some of the use cases that we might choose, but not sure how AI is used here. It's like image classification, convolutional neural network, faulty parts detection in production line. You might be seeing that in factories and shop floors. This is the network. This is the workload that is used for image classification. It identifies, and even the similar thing is used in medical imaging and all those, right? Semantic segmentation, detecting tumors in the brain. Another was text classification, right? And then classify large news articles into a small news bites through contextualization. And text, you can also say text summarization also comes under that group. So flagging offensive social media comments is another thing that NLP task workload is used, and text classification is the category of usage. Text summarization, again, as I talked about this, that there is a work going on wherein a large documents can be summarized into a smaller compact version of the book so that people can still learn, because and not having to read all that, because that, considering that a lot of us are Gen Z, hopefully hopefully a lot of you are Gen Z who are watching my video. We have less. I mean, I'm not Gen Z, by the way, but I'm saying that a lot of Gen Zs have less. They're intelligent, and they have less, I would say, attention span. And that's why, to ensure that they learn, a text summarization is a very useful tool that can be used. Um, you have a lot of chatbots. I don't know why did I say chatbot. Anyway, I will correct it. Chatbot, virtual assistant, or the conversational AI, wherein your natural language processing, understanding, and generation all can be part of it. So Q&A is another area where it is used, you know, largely. Forecasting sales revenue, I just discussed regression, linear, polynomial, whatever, right? So you can use housing prices, again, regression, decision tree, random forest could be there. Speech recognition, RNN, app reaction on voice commands, Apple Siri. So speech recognition is where you Alexa, do this, do that. That's where speech recognition comes into place. Anomaly detection, it's again regression, classifying, clustering. Your classic algorithms actually do a lot of important things, by the way, guys. It's not like, you know, classic algorithms are to yesterday. No, it's not. If you can use these forever, right? So it's used in, say, any kind of anomaly detection. Let's say identifying an unnatural transaction, which would be flagged as a credit card fraud detection. I can say that because I myself have worked on it. Segmentation, clustering, customer, product, market segmentation. It's ideally nothing but your, um, you know, based on certain data points, it's able to. That's a product bundling is also something that you can say is part of it. Dimensionality reduction, visualization algorithm. We'll discuss this later on. Recommendation system, ANN, and then any kind of artificial neural network is recommendation system. Collaborative filtering is also another. Reinforcement learning, I just talked about self-learning robots with learning policy and agents. We'll discuss about that. So ideally, you have a lot of examples, right? So let me just go back one by one. I don't know that decision tree CART algorithm. Again, it's a predicting heart attack for a patient. Knife-wise, fraud detection again in government contract. I'll just give you an example. Support vector machine is SVM. Again, linearly separable data points by class. Don't worry about it. Discuss later on. Association rule mining, it's helpful in product bundling, upselling, right? So, for example, if you see that your customer is buying, you know, a burger, you can suggest, or even a bundle, a product such as Coca-Cola or some kind of Coke Zero with that burger, and give an efficient reduced price. So the customer can buy two products, and you have overall, first of all, a combined sale. Your sales volume is increasing. Your overall numbers are improving, and at the same time, you are able to upsell certain things on that, like you know, on based on what the customer behavior has been, right? So you know that random forest is nothing but ensemble and decision trees. Uh, is again something that can be used for, let's say, median price, um, multiple um, multiple I would say decision trees can be part of that random forest. That's why it's an ensemble method, right? And at the end of the day, I don't know why doing this. Double, what's happening? Right? All right. Okay. So now that we have some basic understanding, right, of where the usages are, let's quickly run through. And again, it's a very quick run through of what are the basic steps required for machine learning, or I would say, what are the basic blocks in an end-to-end ML implementation steps, right? So let's say big picture, what, why, how. This is the strategic planning phase, right? So data collection. So in this is the place time where you are forming all your problem statements. This is a strategy focused step, right? The next is data collection and system design, wherein you actually collect the data and find out what kind of model you should use. By the way, not you will be using. It is your, I would say, strategizing as well along with data collection. So you can figure out, okay, is it if am I, predicting a value? So maybe I will use a regression, linear regression. Am I classifying something, right? So you, based on the problem statement, just you did in the big picture, you will basically collect your relevant data and also figure out the model that you need. Next is EDA. Sampling is nothing but exploratory data analysis and then identifying what ratio you will have. Usually 80% of the data is used for training your model, whatever model you choose, and 20% for testing, right? So that's ideally EDA and sampling, and it's not a small section. It's one block, looks like there are a lot in it, right? So data cleanup and transform. So before you feed your data to the model, and after you have performed your the sampling and EDA, you will have to perform certain steps to clean and treat your numerical and non-numerical attributes. And then attributes means nothing but your features, right? As I just discussed. So you will pick up few models, train them, fine tune them by shortlisting some of the promising models. Then you have finally choose the final model and then serve the model either in a form of app or as an input to another model to be served in an app. You and that your model predicts. You will have the model deployed properly in a specific environment. Could be in a web app, could be in a mobile app, or maybe even an app on some private cloud, whatever your serving strategy was. Based on that, you will monitor how it is performing. Is it still performing well? Is it accuracy still high? Is it overfitting? Is it not? So that kind of ML ops monitoring that needs to be there, needs to have a threshold. As soon as it falls below the threshold, immediately it needs to be improved and deployed, and that way the maintenance keeps on going. Otherwise, the app will stop performing better. And then finally, use the model. Now, are you gonna use it? Are you how are we gonna use it? As in, how are you gonna serve it to the users? As in, are you gonna send them the server through Play Store, or how? Or downloadable from your app, from your own website? You decide all of that. So, right? So that uses the model updated and served, right? So that way you're done with the steps. Now let's talk about what are the different broad categories of ML. Let's discuss. Now, first of all, let's understand how to how to you know categorize these MLs. So we categorize ML systems based on certain strategies, right? What are those strategies? So first, training approach. Is the ML system trained with human supervision? Is it supervised, unsupervised, semi-supervised, reinforcement? Basically, are you providing any reference point for the learning, or basically, are you providing a labeled dataset, unlabeled dataset, or any kind of response system that would ensure the model understands how to, learn? So that's what is called training method based or supervision based categorization. Secondly is the learning mode. Is it learning on the fly incrementally, or is it, full reboot and batch learning mode, offline learning? So offline training basically. So learning mode would decide another kind of broad category of machine learning systems. And I'll talk about each of those. Training method is another. Is There are few training methods. So instance based learning, or IBL, or pattern based learning, or model based learning, or MBL or PBL. What is that? Let me explain um, instance based learning and model based learning. Instance based learning is, you know, comparing the instance of a training data set and learning the difference from reference from new data. So basically, you have a lot of data instances through which you are comparing your image and learning through that. And I'll talk about that in a better way. So basically, model based means, so basically, if I compare it, do you, one example is that you learn by memorizing. Everything that you learn, different data instances, you memorize, keep in your heart, keep in your mind, and you, every instance of the data that you receive, you learn from it. So you basically by heart. There are some students. Even if the teacher sneezes, he or she will even remember the sneeze. There is another kind of student who would not really read line by line, but it would generate a pattern, right? So they are some, it's again like us, right? It's gonna say, oh, you know what? This is following a pattern. So I won't have to remember everything, but I can deduce through this, and I can actually on the spot I can understand based on the deduction, and I can pattern, and I can actually predict based on the pattern. So that is another training method. Both are not wrong, it's just that different. So that is also training method, right? Mode. So that way I can say that there are three categorizations. Now, with that in place, I can say, let's talk about training approach based ML systems, right? So training approach, how much supervision is provided to an ML system? Like a child. Do you tell everything the child to learn? Like when we provide labeled data sets to the ML systems, tell the system what to do and how to think. Example, spam filter, predict value for an outcome, right? Classification, regression, SVM, decision tree, all of that comes under supervised learning. As in, you give them a labeled data set, right? You're providing them a label, and you are able to always, you're sending a comparison, and you're generating the accuracy out of that. So it's supervised learning. Usually when you have to predict a value, you would do that. This is the learning where unmarked training data set or unlabeled to the ML system. So let the system figure it out on their own. Sometimes you're not teaching your child everything from the book. Sometimes you're sending your children for an excursion. Let them understand how things work. Let them meet with other people and learn from them, right? So example, categorization, picking the odd one out, right? So basically clustering, anomaly detection, association rule learning, visualization algorithms, right? So you can say that you have not given any labeled data set. Your data is going to learn from the proximity of the data points and figure out, okay, this looks like these are the three data points which supposed to be together, right? So it performs some mathematical computation and finally gives a grouping of those different affinity based learning, right? So as I said, there are different algorithms which are related to supervised and unsupervised, and we will deep dive in another session on that. But ideally, this is the approach. Semi supervised, it's a combination of supervised and unsupervised. Example, you can snap tagging deep belief networks. Let's say, take an example of, as I just gave an example, right? So wherein you don't tag every image, but then after a few tags, it's able to figure out, right? So semi-supervised. And it's cost effective in a way. There are 1 million images that you need to have a label on. You probably have 200,000 or 500,000 labeled, remaining unlabeled. But based on the similarity of the data points of that images or whatever, right? It's easier for, learning from the labeled data sets. It's able to categorize even the unlabeled data sets. So it's a semi-supervised. Again, reinforcement learning, it's again agent, policy, and score-based learning. Example, DeepMind's AlphaGo player. And even the robotics. Let's take an example, and we will give a little discussion in this topic itself. Is ideally like child if, performs an action, and you have a rewards and penalty system for the child. If it does something good, you say, "Wow, good job." The kid knows, "Oh, fantastic! I'll do it again." Another thing that the kid does is say, "No, don't do that." The kid knows, "Oh no, I shouldn't do it again." So basically, and updates the policy accordingly. That's how babies learn, and learn from wrong, right from wrong, right? So that's how reinforcement learning works. Now, there is a lot of technicalities to it, but this session is not fit for that. Let's talk about the mode of learning, right? So let's say batch cumulative offline learning. In this mode, learning is not automatic from the data feed on the fly incrementally. It needs to learn the whole data every time. So it's definitely cannot be offline. Cannot be online. It's offline learning. It's like you take down the application, you take down the whole, you repaint, you take down your doll and you repaint, re-image everything, and every new learning that coming at one shot again on top of what she has learned. It's a entire full refresh of the learning, right? And it's, of course, it cannot be done real time, so it's a batch anyhow. So ideally, it's not very effective, but in sometimes it may be needed considering the kind of problem statement that you're dealing with, right? So it um, requires more time, compute resources. Of course, you have to do a full refresh. You need to take downtime. It gets trained, gets deployed, and then starts predicting again. Doesn't learn until you retrain the model again, and may predict outdated. Like as I say, ChatGPT 3.5, it was predicting outdated because there was no refresh in those. Retrain means new version of the AI app, as in may involve downtime for replacing the old model version, right? So it's kind of spooky. I would say a lot of things involved. Automation has to be there, without which, if it's a manually, nobody can deal with too many jazz, right? So forget that. I don't know what happened. Okay. Now, on the fly, incremental online learning. In this mode, data instances are fed in sequential mini batches as it arrives. So, delta learning, on the fly learning, incremental learning, and online learning. So, faster, needs way less compute resources. Let's take an example. Your model is able to learn from by crawling the Google sites, sites available through Google. So, which means it's learning delta, it's learning incrementally, and it's learning on the fly, and it's online. It's not something that once fed in, nothing else can influence. It can be influenced. So it's more dangerous, but more effective. The model gets trained on the fly, keeps getting latest data to predict by. So you can trust this model more. Even though if there is a crap in the sites, then there it will feed crap. So you cannot predict. You cannot say that it is very accurate all the time. Each training is not dependent on downtime. So since it's coming like learning as we go, you don't really have to take your model down and kind of, you know, dismantle everything, reinstate. No, you don't have to do all of that. And automation is efficient, of course. If you're dealing with the large data instead, and that's the reason why you need to go offline, because it's large data that you're, loading back. But let's say if you're eating a small batches of data, it's really not a big deal on the system. So ideally, it's again efficiently automated, right? So high learning rate, of course, learning rate is high, may forget older knowledge, fragmented learning. So ideally, you know, if you have, since you have no control mechanism, which is why sometimes people want to keep the control mechanism and kind of keep it offline. But if it's high learning rate, it's possible that what what something that it was predicting yesterday, today there is a change for whatever reason that has been updated, right? So it is now saying something else. So there's, you know there is a change. There is a, I would say, let's say an app, an AI app that tells you political summary, political news summary. It's completely different summary can come up here if somebody kind of, if the net, online behavior outside is different, it's going to behave accordingly, right? So low learning rate, learning interior in inertia takes place, not sensitive to noise, may even consider outlier. So basically, as I say, um, if it's the learning rate is high, then it will start updating anything. If the low learning rate is low, then it's kind of pick up, I would say, unverified information as well as its input. So let's talk about how a model can predict with a new data set given to it. Ah, right. So let's talk about the learning method, how the ML system is generalized, how a model that can predict with a new data set given to it. So let's talk about IBL, instant based learning, memorize by heart. All examples. Learn every example possible and predict based on that. Limited by example, right? Requires measure of similarity, as in how similar is similar. Needs to have that understanding. Mostly based on affinity, grouping, clustering, right? So it can relate with clustering algorithm. Now, before I start with model-based learning, as I was giving that example, right? So I remember we had while I was doing my engineering, there was a student. So a teacher was giving lecture and she was taking notes. When I went there, and I was usually the one who was the second type. I was not so much into learning everything. So I went back to her, said, "Can you give me the notes?" She gave me the notes, and I saw that she has drawn a fly. I said, "What is it? What what is it? Why this fly is here?" She answered, "There was a fly on the board." so, so she copied everything possible and memorized by heart. So, did she perform well in the exam and was able to perform great? Yeah, she did. But her method of learning was different. Whereas another approach is model based learning, wherein I really don't want to build a model from examples. Like, I don't want to take information overload. What I want to do is establish a pattern, right? So I need, yeah, this, right? So if I have a pattern that's well observed pattern, I really don't need like, for example, some one student thinks there are 100 example maths, and he or she practices all 1,000 or 100 or whatever number of math questions, considering she's hoping one of them will be known to her. So she has done, it's a good thing, practiced well. But at the same time, another student is thinking, okay, I need to just learn 10 different patterns of math, not all 1,000. So if I know all how to tackle with all 10 different identified patterns of math example, and if I know how to deal with this on the question, during the exam, I will be able to anyway answer remaining. So both scored high. One scored because one practiced thousands of examples. Another learned because, another performed well because she or he, or basically in my case, I was able to pick 10 different categories of mathematics questions and was able to confidently deal with it. So even if there was unknown math, I was able to deal with it primarily because I knew the pattern, right? So detects a pattern, model gets trained on the fly. So I don't really need to know all the maths and their answers to do better. So that's the second category. Each training is not dependent on a downtime. So the effort that I need to do 1,000 maths, I would need way less effort to learn 10 maths, 10 working, examples. Automation is efficient. It was easier for me to remember. And I was done. Well, I eventually scored more than her a little bit. So the point that I'm trying to make here is that these are the two methods of training your models, right? Now, there are some, I'm not going to read out all of these because I probably will have classes around each of these algorithms, but these are few basic algorithms that you can see in the both supervised and unsupervised categories. Like supervised, you already know what to pick out of the data sample and you need labeled data set for building the model. Classification, you see some naive-Bayes, KNN, support vector machine algorithm, or SVM, decision tree, random forest. There are some optimization algorithms. There are within regression. There are in the regression is another neural network. Some of them can be called up under supervised. Similarly, unsupervised is where you do not know what to label on. So no label data sets needed to categorize, and data may follow unpredictable pattern and but distinctly different patterns. So like clustering, anomaly detection, visualization, association, rule learning, all of this can come with that. Now we go deep detail level on all of these as we probably proceed. Right, so that's where we are. There are some sample examples based on the category of task in each of these that I have tried to mention, such as email spam filter, credit card fraud detection, text classification, image classification, all are coming under the classification, and it's classified based on existing reference data. So ideally, it's a supervised learning. Similarly, regression, wherein predicting a value, it could be housing price, risk assessment, risk score, vulnerability analysis, uh, key influencer identification. All of this will be can be where I'm predicting a value is a regression, and again compared against a reference point, which we call it as a label, and that is basically falling under supervised learning. Similarly, there are some neural networks or deep learning tasks which are like image analysis, semantic segmentation, speech recognition, handwritten character recognition, facial recognition. These kind of come under, I would mark them as supervised, right? Even though it is neural, neural network, but it does have a reference point to look for, right? So that's why these are. So we have some unsupervised as well, wherein we are finding different categories like clustering, client, product, market segmentation, right? K-means clustering can be used here. Anomaly and novelty detection, as in a little behavioral disorder, an aberration, a deviation from general behavior, outlier detection, right? So all of these coming under the unsupervised learning, because you really don't have, it's like you don't know what it is. Like, sometimes we say, well, I have a feeling it's bad. I just don't know what it is, but I know it's bad. So I think you have already identified that it's grouped into a category of meanness, but you don't know, you don't have a reference point to calculate how bad it is or whether it's really bad. So credit card fraud detection, like it's an unnatural transaction. It may or may not be bad, but looks like it's a very unnatural transaction. So I think we need to flag this, right? So faulty part detection looks like the part that I see in my when a while in my imaging. I'm seeing that the faulty part is looks like deviating from other parts, right? So it shouldn't. It's mathematics. Sorry, it's a you know manufactured element. It shouldn't be an anomaly, right? So behavioral suspicion. Somebody is strangely walking about. I don't know if the person is just like that or maybe something suspicious. So ideally, these kind of um, anomaly detection is also coming under unsupervised learning. Association, fidgety, sometimes criminal behavior. And again, these kind of analysis may go wrong as well, guys. That's why we'll talk about that, the responsibility of AI. And association rule learning, it's nothing but kind of clubbing together, like market basket analysis, and analyzing the images of the products in the production lines to automatically classify faulty products, right? So that's kind of you know supervised learning. And sorry, I think it's wrong. Market basket analysis is where you have a specific customer behavior based on which that what would be your next upselling opportunity with that customers. We discussed that. Right. So AI ML algorithm example, I was just discussing the reinforcement learning, wherein there are two elements to in this learning environment. One is the environment, or on these there is the learning engine. So let's say for exploration exploitation, right? So it's like I don't know what to do, but I'm trying and exploring. That is exploration. And exploitation is I've already learned it, so I exactly know one. Correct action, yay, correct action, brownie points. learning agent strengthens that. I got it right. So strengthens, reinforces, reassure the policy. Incorrect action is correct and updates the policy. It's a penalty, plus 4, minus 4, right? So robotics, manufacturing, recommended systems, marketing strategy definitions, what works, what doesn't work, right? So faculty and facility management and alerts. So ideally, these are the areas where this reinforcement learning, so basically saying perform an action and learn from your mistakes. So that's the learning method we have. Now, it's a very important area. Still, I like to talk about it. Let's say how do I ensure that? I mean, why the responsible AI, the term that is these days very much. I would say it's going on too much, right? So finally, so AI is growing at scale, and AI is becoming a common, and hence a governance needed for a responsible AI. So we give roughly 5 pillars for AI governance. So what are those? So first of all, it's a bias. So ideally, it talks about, is my prediction biased? I need to be careful whenever I'm, let's say, an app is being rolled out. I need to be careful about my prediction. Is it biased? Right? Selection bias. Selection bias is what? Let's say, take an example. When you have sampling bias, right? When you have trained your model that does not have the representation from all different kinds. Let's take an example. Let's say in a delinquent app, it shows that all the Spanish, let's say in a delinquent loan delinquency checker app that is rolled out in the United States, and it identifies all white people are good to go, and all black and Spanish people are rejected. So ideally means that the training process is biased. Maybe the training data sets are only identified for people who are delinquent and dark, and probably white people are only represented with high income category and high, uh, you know, low delinquency score. Who knows? But the point is the data point, the samples are non-representative of real data points, real data scenario. So it's a selection or sampling bias that can say, right? So, or even that's, it's an app's responsibility to be sensitive to ensure that these kind of bias is not there. Another is implicit bias. So let's say when your data has limited outlook, right? So your model confuses between a tiger cheetah, with a cheetah print jacket. Why? Because your data has limited out. You only trained your bias, your model, to know how the prints look like on the screen. You haven't trained your model to figure out other features like shape, size, you know, all of that. So it's not shape, size, is there any eye available, and all that. Figure out. So what I'm trying to say is that it's a bias happens when you have a very narrow outlook to the data. So it's an implicit bias that you could say. And also another example could be, um, let's say you have informed, you know, you're asked to form a football team, and you have created two football teams, one with all short boys or girls, and the other with all tall boys or girls. So even you not realizing there is a bias. You have created two different groups with two different structures. So ideally, it's not a fair grouping, right? So ideally, you have an implicit bias. Reporting bias is another approach. Reporting bias is where your model learns from social media, and by observing different influences, it thinks some opinion is correct just because it's fed it frequently. For example, um, your model is always going to learn from a site where racial statements are made and those kind of comments are there. Ideally, since it doesn't know better, your model will start actually learning those comments as true emotion, right? For example, so if your model is learning from a system that is not wide enough and it's very narrow, again the narrow focus and limited learning avenue, that would lead to reporting bias. Finally, you have group bias. Group bias again is what, as I was just mentioning, when you have a smaller focus group, like let's say your model learns from only a site of terrorism. Just giving a bad example. At the end of the day, it's going to be a model that thinks terrorism is normal. But then, because you have only sent into those focus groups, right? So your group bias has made your model build an build an opinion, or let's say it learns from a focus group that every African is thief or every Indian is thief. In a lot of Western countries say so. A lot of I wouldn't say lots of countries. I would rather say some hate groups say that your model is only learning from those sites. It's not going to develop that on any other opinion. It's like your child. You send them to a wrong school or a wrong group of boys or girls. They're going to come back with a very harsh outlook in their life, right? So, similarly, group bias, right? Similar accountability. Now, this relates to the ownership of consequences of a decision based on the prediction. For example, I cannot run away from what I predicted. Let's say I predicted somebody is this body shape, body color. This is the dress. So this person is a shoplifter. And then that person is going to get, arrested as a shoplifter without any proof, because the app says so. I have to take an accountability of that app saying that, right? I cannot, run away from that. Because at the end of the day, because of that app, and today AI is everywhere. If we have developed an app that does not predict the right person for the right cause and with the right associated task, and lives are altered because of a bad decision, because judiciary systems are using it, right? I am accountable as an app owner or app user. We all are accountable for those, right? Explainability. If somebody charges back and say, hey, you know what? How your app marked this person as a shoplifter? Well, I have to explain. I cannot say, oh, I don't know. My app did it. Some algorithm. No, I need to be able to say exactly how. What are the data points that I've used to kind of come to this? If it's right, if it's right. If it's not right, well, hello. Then the app can be banned. The app owner can be charged. Things like that. So reproducibility. If my app is suggesting something, right? My model is suggesting something, it needs to be replicable. Cannot be like, okay, last time when I checked, this person was identified as shoplifter. Today he's identified as a doctor. No, this must be replicable each time. Cannot be random ad hoc prediction, because that's dangerous, right? And that's a useless app. Robustness, right feature to predict. Now let's talk about it. Let's say, it's a funny example, by the way. Let's say you have a self-driving car and you have to ensure that the car is able to detect objects in front of it without any supervision, right? Now you are trying to make that car recognize a field by, detecting a cow that was there in the field. Well, today the cow is not there. It's not finding that field anymore, right? So it's stupid. So you cannot have such stupid features to train your. You need to have a right selection of features, uh, you know, to ensure that your robustness is protected. And because when it comes to self-driving car, lives can be threatened. It could be life-threatening impact if there is a problem in detection of the object that the car is supposed to detect, right? Secondly, privacy. So as we know that as the days go by, and we have a lot of work to do, and we are deploying AI almost everywhere. Even should I get married, people are trying to use AI in that. Ideally, this is done by, I mean, today's, and I wouldn't say today's marketing driven or marketing flooded world since probably 1960s. It's like that. So if that is the case, then, as of today, for that same marketing enthusiasts, we have given them tool to collect data from people when they're passing by. There is nothing as of today that is hidden activity. You search for something, tomorrow you will see everywhere, against your name. And on your devices, it is popped up. And let's say you have shared your screen, you know, and people would say, what are the products you search? Probably you search for innerwear, and that is everywhere appearing on your page. So, it's normal, it's bad. But at the end of the day, this needs to be controlled. What data can be collected, what data can be processed, and what data can be served to you or anybody else around you, right? This needs to be controlled through data protection and utilization laws. It's not 100% at the moment. Well, there needs to be a proper consent law, which also doesn't. There are a lot of data that we give away without even a consent. So that is also another important aspect in responsible AI. I mean, AI has to be something very importantly taken in our lives. It's a beast that has to be well controlled. I mean, when I say controlled, I don't mean taking away its ability to a point where it's unusable, but a censorship must be implied, or rather, I would say governance is the right word. Not even censorship. Governance is the right word for ensuring the privacy is not invaded while I'm using the AI. So these are the few governance pillars through which we can actually use AI responsibly, right? So that's it, friends. I think have a great day. Oh my God, I need water. Thank you.